G'day chemistry students. In this video we start module 8, which is called Applying Chemical Ideas. As its name suggests, we'll be focusing on taking a lot of key concepts that you've been learning about through the entire course from modules 1 to 7 and applying them to much more real context rather than theoretical ones. That's going to mean that there's going to be lots of practical activities at play. It's also going to require you to reflect back on a lot of the work that we've already done to actually begin solving chemistry problems. Now, primarily the content that we are focusing on in this module deals with a branch of chemistry called analytical chemistry. It's not something that we focused on a whole lot while we've been doing this course. The one time that you're probably most familiar with what analytical chemistry is all about is when we did titration all the way back in module 6. When we're doing titration, the whole purpose was to analyze an unknown substance to determine its concentration. Generally, analytical chemistry can be broken up into two parts. One is if we know what the chemical is, but we don't know what the amount or concentration is, we can go through some analytical techniques to find that out. So we'll be doing some more techniques to find concentrations of unknown substances. But we're also going to be learning some techniques that can be used to identify unknown chemicals themselves. So if I have a substance, I have no clue what it is, we're going to be trying to figure out exactly what that chemical actually is, what its species is, if it's an organic chemical in particular, what kind of structure it might have, etc. So let's get into today's first lesson, which is all about spectroscopy. And in particular, my focus is going to be on infrared spectroscopy. Now, spectroscopy itself is used to do exactly what I just talked about a second ago, which is identify unknown chemicals. In particular, the first 4 videos for this module are going to be all about spectroscopy techniques, which can be used to identify organic chemicals specifically. Now, for these techniques, there are applications for use in the inorganic chemical world, but it will not be a focus for this module in particular. We're really going to be looking at identifying organic chemicals again for these first 4 spectroscopy techniques that we are learning about. So first off, let's look at what spectroscopy actually is. Essentially, you're measuring the interaction between a chemical and a source of energy. So if I shoot some sort of electromagnetic wave at a chemical, it's going to respond in a variety of different ways, depending on whether we're using radio waves, infrared waves, UV or visible light. The chemical will behave differently. And in particular, different chemicals with different functional groups or different structures will behave differently when exposed to different wavelengths of energy. So if we have a machine that can produce those wavelengths that we want to analyze with, and we can take measurements and record them using our knowledge of spectroscopy and how different types of chemicals respond to different waves of energy, we can identify chemicals and their structure. So there are 4 techniques that we're going to be using. Mass spectroscopy is a little bit of an exception to all of that stuff for spectroscopy that I was just talking about. Their energy source is high energy electrons. And so rather than having the molecule itself interact or behave in an interesting or different way, the bombardment of electrons will ionize the substance and will also split apart and break up the molecule into fragments. And we can analyze that to be able to figure out the size and the structure of different parts of the molecule. We also have NMR spectroscopy, which uses radio waves, IR spectroscopy, which we'll be talking about today, which uses infrared waves, as well as UV visible spectroscopy, which fittingly uses UV and visible light. So when we're using spectroscopy, what we're trying to do is interpret a spectra, which essentially is a graph. The graph that is produced for each of those 4 techniques look very, very different, but we use and interpret those spectra to identify an unknown chemical. We may also use spectra. In particular, we're going to be using UV vis spectra to be able to find the unknown concentration of the chemical like I alluded to earlier. So when we're interpreting spectra to identify an unknown chemical, these are some of the graphs that we are going to be looking at. This is a pretty characteristic IR spectrum. This is a spectrum that we see when we do mass spectroscopy. And these 2 ones here are for NMR, or nuclear magnetic resonance. There's one that we can use when we're focusing on carbon atoms, and there's one that we can use when we're focusing on hydrogen atoms. So first off, what I really want to talk about is this idea that frequency or wavelength is not something that I'm going to be talking about a lot. I'm going to be comparing different kinds of waves by their energy. This comes down to a very common physics equation, E equals hf. This is the energy of a wave, and what we're saying is that the energy that a wave carries is related to the frequency of a wave. Planck's constant here, just like other constants that we've used in this course, are there just to act as a mathematical bridge between the energy value and the frequency value. You don't have to do any calculations with this equation in this topic, but what I do want to really highlight is things with low frequency on this side have low energy, and things that have high frequency on this side of the spectrum have high energy. And that is something that you can prove mathematically, but you're more than welcome to do that yourself. Usually what we'll see is that electromagnetic spectrums are like this, from low energy or low frequency to high energy and high frequency. Again, just a different version of really the same concept. Our focus today is going to be looking at infrared energy. So when looking at infrared waves, what we're looking at is how those waves can cause vibration in the bonds between atoms. Now, for an organic chemical and any chemical, as long as we're not operating in absolute zero temperature conditions, we can always see that there is going to be some amount of vibration between molecules. This is just something that naturally happens because there's energy all around these molecules at all times. However, if we were to add some additional energy through infrared radiation, what we can start to see is that for particular frequency, the vibration that we see will become larger. The extension of the bond will become larger and the compression will become shorter, essentially a larger amplitude vibration between the bonds. Sometimes we see that as stretching, so a stretching action. This could be what we call symmetric or asymmetric. We may also see bending of the bond, so either a scissoring motion or a rocking motion. Distinguishing between these is not something that we really need to focus on in the course, but I did just want to really highlight that the bonds can vibrate and interact and behave with this IR light in a variety of different ways. So not all bonds will actually interact with all wavelengths of infrared light. What we actually have are resonant frequencies, and this is a frequency which causes the largest amount of oscillation in the object. And usually what we say is that their frequency matches the object. So with sound, a lot of the time we talk about resonant frequencies with musical instruments, and something that you may have seen or heard of before is how sound frequencies can resonate with glass, making it vibrate at its maximum and causing breakage like we can see in this GIF. Similarly, we can have matching objects where our objects are the different kinds of bonds that we see in organic substances. So for example, bonds between carbons will resonate with a different set of infrared waves compared to the oxygen-hydrogen bonds in an alcohol. You'll notice here that all of these numbers are measured in what we call a wave number. I'm not going to go into a large amount of detail about how we get this number, but just know that the wave number essentially comes from the wavelength of the infrared light, and we can convert wavelength into frequency and convert frequency into energies. So what we can say is that the energy, wavelength, or frequency of the infrared light has a different resonance for each type of bond. And so the amount of energy that we need, or again, the frequency or the wavelength that we need, is going to depend on the strength of the bond, the length of the bond, the atomic mass or size of the atoms in the bond, as well as whether we have single, double, or triple bonds. So when using infrared spectra, we can refer to a table like this. You find it in your chemistry data sheet to be able to identify areas of the spectra which are showing up with some sort of trough. So for example, this little trough here is in the region from about 2,700 to 3,000, which fits quite nicely into this range here, probably implying that the trough that we see is due to carbon-hydrogen bonds in this structure here. We also see a trough at 1,716, which matches up quite nicely with our carbonyl group, our C double bond O, again, which is present in the molecule that this spectra was taken from. You'll also note that this region here starts to get really, really complex from about 1,500 and below. We call this the fingerprint region. Reason is that you're getting resonance from all sorts of different bonds, mostly carbon-carbon bonds. There might also be some carbon-hydrogen resonance that's happening here too, And because there are so many different kinds of bonds, different lengths, we end up getting a variety of different troughs. And so for the human eye, it's very difficult to actually get any information out from this fingerprint region. We're expecting to see something because there are carbon-carbon and carbon-hydrogen bonds that are present in this region, and that's completely fine. But really, the only way that any of this data in the spectra could be useful is if a computer was able to match the spectra that we got to a database that already exists that shows essentially, again, that fingerprint for each different kind of molecule. And we could possibly use that then to identify the molecule that was scanned, but not something that we're going to be doing in this course. We're not using computers to be able to interpret these spectra. We're learning skills to interpret the spectra itself. So generally, we're going to be looking for troughs that exist between 1500 and 4000. And that links up quite nicely with most of the different kinds of bonds which are highlighted in your data sheet. Just wanted to show you a couple of pictures of infrared spectrometers themselves. Usually they just look like boxes, and in this spectrometer here, what we can see is that the sample goes in here and there's actually a beam of light that goes through. This would obviously be closed just to make sure that any interfering energy isn't coming through. But yeah, we can pass a beam of light through here to be able to put infrared energy into our unknown sample. This is a schematic of what's actually sort of happening on the inside. We don't need to know every single part that's here. I'm just going to highlight some bits. Obviously, there's going to be mirrors moving the infrared light around. We have an energy source, and that energy source goes through the sample. Once it gets through the sample, what we can do is use something called a diffraction grating to split the light up into its different wavelengths. So the diffraction grating can let all of the wavelengths through with all the wave numbers. So in our case, like we saw in the graph previous, we can go through as many of the wave numbers from say 500 to 4000 as the machine will allow, and measure the amount of infrared light that's actually going through the sample and all the way to the detector. Once we measure how much light gets through, the signal might get amplified potentially, but then actually recorded and produced as a graph. So what we can see here is at the top parts, most or all of the infrared light went straight through the sample cell and it didn't resonate, and that meant that none of the light was absorbed, so it got all the way from the energy source to the detector. However, these places where there are troughs, what that suggests is that there is resonance for that particular wave of infrared, meaning that as those particular wavelengths of infrared light hit the sample cell, a lot or all of that energy was absorbed, meaning that a reduced amount of that particular wavelength of infrared light hit the detector, meaning that there was a drop in the amount that got through. This is a little bit more of a simpler version of that diagram. If you were ever asked to draw one, this is the kind of diagram that I probably go with. Now, the last thing that I want to talk about is this idea of being able to calibrate your IR machine. Some IR machines will have a reference, some of them won't. We can sort of have a calibration step in the same way that we tear a balance if we don't have a reference. But the idea here is that your sample is not the only thing that the infrared light is passing through. Also, the bulb that you have for your infrared light source may be brighter or dimmer depending, so you always sort of need to set up your infrared spectroscopy before you actually do it to account for all of those variables. So what we can see here are lots and lots and lots of different infrared patterns that exist, and these were taken all at different times. Essentially, there are molecules in the air, such as water vapor or carbon dioxide in particular, which will resonate with infrared light. And depending on how much water or carbon dioxide is in the air, will have an impact on the amount of the original infrared light source that actually gets absorbed at each of those resonant wavelengths. Something else that may end up absorbing infrared light is the thing that's actually holding the sample itself. And these are all things that need to be taken into account and essentially wiped from that final IR measurement. So for example here, water causes a lot of interference across the entire infrared spectrum that we use for infrared spectroscopy. So what we would want to do is take this sort of as a recording as well as any other interfering sources and tell the machine essentially to set all of that as zero. Whatever's already being absorbed, however much is getting through, set all of that to zero so that we only take into account the organic substance that we're actually trying to analyze. So for infrared, what does it actually tell us? What can we use to be able to identify the unknown chemical? Well, the troughs that we've been looking at can be found in the spectra and analyzed, again, using a reference chart like this, in particular, one in our data sheet, and we can use that to identify the functional groups that are present in the unknown substance. For example, if we find that we have an alcohol, because there's a characteristic trough that's there, that's not really going to tell us whether we have methanol, ethanol, butanol, propanol, pentanol, octanol, etc., nor will it tell us the location of the alcohol group either. So as chemists, we can't just use infrared spectra to be able to determine all the characteristics of a substance, but knowing that we have an alcohol is a really good first step. What we may need to do is use other analytical techniques, in particular other spectroscopy techniques, to find other information, again, about the size of the molecule, its chain length, the position of the alcohol group, etc. Thank you very much, everyone. In the next video, the next technique that we're going to be looking at is mass spectroscopy. This technique gives chemists a lot more information about the size of molecules that we're analyzing, as well as their structures. But until then, have a good one.